Hello, I've done a few videos recently on the Wilcoxon Rank sum test, so much so that I feel like it's worth doing a single variable Wilcoxon Signed Rank test to distinguish between the two. Signed rank tests can be used for paired tests, but only paired tests with two sets of data, or for single variable data where you're comparing a set to something, either a change or a comparison to some other set which you've not been specified or whatever. So here we have a question. It's from actually an old, well, it's not that old, but it's from the old syllabus, MEI syllabus on S3, which is on Wilcoxon Signed Rank test. First of all, the question is a little bit helpful, and it's told us to do the Wilcoxon Signed Rank test. The only alternative here would be a sign test, the kind of one which uses a binomial, which we would use in circumstances where we can't make the assumption that it's symmetrical. But this question hasn't really dealt with that at all. They've just told us to do the Wilcoxon signed rank test, and that is it. So that we don't have to consider whether we need to do that one or not, because it's told us. So presumably the data, the population of the population is symmetrical. Otherwise a Wilcoxon Signed Rank test wouldn't be appropriate. So the first thing to do is to set up the hypothesis, which I've just quickly kind of prepared here. We need to basically basically need to define our variables, which you can do in words. But M is often used for median, so I quite like to use M to signify median. It's two-tailed because it's one-tailed, sorry, because it's looking for larger, so that's one-tailed there. And it's basically what we're doing is we're comparing, we're basically doing a hypothesis about South American fruit flies and comparing them to European fruit flies, which we know the mean or the median is 2.5. We know the median is 2.5 for the European fruit flies, so therefore we are comparing to that. And the null hypothesis is that the South American's also 2.5, and the alternative hypothesis is it's more. But we need to define what we mean by median as well. And the population is also an important word to include here, because obviously a hypothesis is always about population in these situations, in these tests. Okay, so now let me get on and do the test. Okay, so let me just bring up the data there, hopefully again. Right, okay, so what we do is we look at the actual difference between the difference between the data that we have and the median that we're comparing it to. So the median is 2.5, and so we're just finding the difference and ignoring the we'll do that a bit later, but we're not ignoring, just finding a difference from 2.5 positive or negative. So for example, the difference of the 1.7, that's minus 0.8, whereas the 1.4 is minus 1.1. And the 3.1 is actually plus 0.6. And so on. Okay, so then what we do is we rank them, ignoring these, well, just being aware of the actual, ignoring the sign in the first instance. So let's do that. But then actually we'll kind of retain the sign later. But let's just ignore the negative. So how, first of all, so rank them. 1 is the closest to the 2.5. And then the next closest appears to be the 0.3. Yes, minus 0.3, but we're ignoring the sign at this stage, so that's 2. And then 0.4, that's 3, and so on. So then actually what we do is write the signed rank, and I tend to just do that afterwards. So signed rank, don't attempt to put the negative in whilst you rank in, just ignore it. So signed rank, basically what we do is we take any negatives, we just then kind of re-establish in the numbers for our rankings. Like that. So we've got the negatives and the positives. So then, and this is all described to you in the formula book, by the way. It says it's all fair. W plus is the sum of the ranks corresponding to the positive differences, and W minus is the sum of the ranks corresponding to the negative differences. So the sign of the W plus is equal to W plus equals to the 4 plus the 7 plus the 9 plus the 11 plus the 3 plus the 12 plus the 1 plus the 10 and the 5, which comes to 62. And the W minus is the negative ones, but kind of now we actually modulate it again, so it's the magnitude of these. So it's -6, -8, -2. So that's equal to 16. And then so the test statistic, and again it just remember that they call it T in here, so T is the smaller of W plus and W minus, so T test statistic equals to the 16 because it's the smallest. Okay, and then what we do is we actually see whether we're rejecting or accepting the null hypothesis. Now the sample size here is 12. It tells us in the question 12, and you can count the number of data values is 12. So we look for the critical value with a sample size of 12 at 5% one-tailed. So we're looking for 5% one-tailed. So 5% one-tailed with n equal to 12. So let's have a look. So one-tailed 5%, so we're in this column, with n equals to 12, so that the critical value is 17. So the critical value is 17. So we're actually below 17. Now 17 is the number, basically the smallest that we would reject the null hypothesis. So for example, 18 we would not reject it because it's too big, but 16 is below, so we reject it. So 17 the smallest, which would reject the null hypothesis. So because T equals to 16 is less than 17, which is the critical value, we reject H0. And now we just need a contextual statement, which is something like there is sufficient evidence, and we need uncertainty, as I always say with these things. No, nothing definitive. We do not say they're bigger or, you know, anything too brief. Either there is sufficient evidence to suggest South American fruit flies, the median length of South American fruit flies is larger than European fruit flies. Okay, so that's it. Right. Fairly simple when you know how. I hope you found this helpful. Just follow the process with these things. It should all work out fine. Thanks. Bye.